Thank you. Yeah, so I guess we start. Yeah, so hi everyone. Again, my name is Eugene Lyapustin. I work at Yandex, and we're building a diffusion model for image generation called Yandex Art. So about Yandex, for those who don't know, Yandex is a big tech company in Russia that has a widely used search engine and a wide variety of services like taxi, delivery, electronic commerce, and more. And so we here can do much with image generation in our internal services. But let's dive into the topic. So what's a diffusion model? Imagine you have an idea of a dragon kitten, and you want to get a picture of it, something like this. And in the past, to get this image, you either needed to search on internet for it, maybe draw it yourself, or commission an artist. That all takes a lot of time. But today, you can use some application like our Shedevrum or Midjourney and type your prompt and get your image like in seconds. But how do they work inside? Every image generation model nowadays start image generation with just pure Gaussian noise. And we have this diffusion model that is trained to step-by-step denoise our model and add some features that correspond to the textual description you gave it. And we do it for several steps and get the final picture. And so the model is trained to, from each noisy image, predict the final image given the description. And inside, well, in the past, all diffusion models work like this. It was a UNet, but with attentions inside it to reuse information from textual description. Nowadays, many industry models use transformers for diffusion, but in our experiments, UNet worked better. And so we have it, basic pipeline. When we have our textual description, we give it a diffusion model. It denoises, it kind of iteratively makes denoising and produces final image. Usually it's more than 3 steps. It's 30 steps, 50 steps, but let's stay with 32 steps. And because of this iterative nature of diffusion models, we can use them to modify images. You've probably heard that Stable Diffusion can do inpainting, modifying images, remixes, and that's all because of this iterative nature. But this pipeline is not full. First of all, we don't want our diffusion model to learn about text grammar. We don't want it to learn different languages. We want to give it some already processed complex information about the description we gave it. And so everyone uses something called text encoders. It's usually text part of the clip, like our architecture, or some textual encoder, like T5, for example. And so we process our text prompt using text encoders, and they produce something we call embedding, like some more complex representation of the given prompt. And diffusion model conditions on this embedding. Then the next problem is that if you want to generate an image of high resolution, for example, like 1000 by 1000, it's really computationally hard. Firstly, yeah, it's hard to inference this model because you need a large GPU to, just make an inference one step of this, the whole process. But even more computationally hard is training such model because we want to train our model on as much images at the same time as possible. And for some models, it's even impossible with modern hardware to train a model that produces such high resolution image from just pure noise. So here's the trick that everyone uses today. There's another separate neural network called variational autoencoder. And it consists of two parts, encoder and decoder, and it is trained to firstly compress our image into something smaller called latent, so it's just some sequence of numbers. And we have another part of the network, decoder, that is trained to reproduce from this latent original image as accurate as possible. And this network can be pretty small and pretty fast compared to diffusion model. Just for analogy, you know of PNG and JPEG, it's algorithmic compression, and this variational encoder, it does compression by neural network, kind of similar. And the trick is that instead of our diffusion model generating an image, we're training it to generate this latent. And then after the model generated this latent, we can, with one step, very fastly, decode this latent into the final image. How do we train it to produce latent? We take our whole training data set, and we encode all images using encoder, and we get a data set of latents. And we train diffusion model to produce them. And so probably most of the image generation models out there, DALL-E, Flux, probably Midjourney, they use the same whole pipeline, and our model Yandex.Art as well. And the next step is we need to train this diffusion model. We won't discuss variation of encoder and text encoders, they train separately. We'll discuss how we train a diffusion model. So, of course, if you want our model to generate pretty much anything we can come up with, we want it to see everything during its training phase. And for that, we want to take like some huge chunk of the internet and train the model on it. In our case, it's hundreds of millions of images, closer to 1 billion. And that's like the source of the data set, the internet. Also, we need pairs, like we don't need only image, we want also an accurate description of this image. Like if it's a dragon kitten, we want to see what color it is, what's in the background, so diffusion model can learn to predict them in the inference. And so there are several sources. We have a large search engine inside company, so we have a huge database like of hundreds of billions of images. But it's quite noisy. There are a lot of low-quality images, compressed images, and also the text that corresponds to this image in the internet, it can be also quite noisy. It just can be some random news or a pure description, but at least we have some images. For text descriptions, we also can use search queries when users use our image search. They type some prompt and they find some images, they click on it, and we can make a pair from that. But yeah, it's kind of biased because if a person looks for a cat, there will be just some random cat and just description a cat, not very descriptive. The third option, we can take like any image and we can use some visual language model or just any captioner to produce a description for it, not only. So we have just an image and we get a description of it. So it's a third option. And the first option, there are a lot more stuff that we can get a dataset from. For example, when we already have an image generation model, we can use, we can take logs from what people generate, take their descriptions, and pair our model generation with the description, and maybe train the next version of the model on our generations. As I said, these images, they're also quite noisy, so we have several steps of filtering to get more clean data set. First of all, we remove images that are too large or too small, because small images, they are low quality, and large images, it's hard to automatically resize them or crop them to get an image of good quality. Then we, of course, remove all duplicates, so we get one image instead of a number of similar ones. Remove not safe for work content, and we have several trained classifiers by which we can also filter out some low-quality images with low aesthetic, maybe compressed ones, and of low details and more. And after that, we decrease our database by 100, and our final image database consists of 1 billion of images. Here, for example, on the left, it's a sample from the original 100 billion images. They're kind of strange, and we don't really want to generate most of these images with our diffusion model. And after all the steps I described before, we get a sample from that, and there's more what we hoped for. It's more clean, and these images we want our model to generate images like this. The next part is textual descriptions. As I said, each image in the web usually contains some text near it. For example, this is just some random image from the internet, and there was a text near it. My perfect Lamborghini Hurricane Spider, right? But this textual description is not really good for training a diffusion model because it doesn't really describe this image. It says what model a car is, but it doesn't say what color it is, how it is located, where it is located, what's in the background. So we want something better, something like this. This description we generated with our internal visual language model that took original image, original text, and improved this description. After that, we get that a sport car is white, it has a black top, red seats, it's parked in a white background, and it's much better for the model to train on. Because after training, our model better corresponds to what you type in. Yeah, so then we have this billion of images. We generate captions using our model, using our visual language model for all of them. And we train our model on hundreds of GPUs for like a month. Actually, we have several training stages. First, and maybe the main one, is called pre-train, when the model learns about the world, learns about all the concepts of everything that you could type in. It should learn from this stage. And this is the stage, the longest one. It takes like around a month. And after that, we get a model that can generate images like this. So we have a prompt on the top, a small house on a mountain top, and the model generates images like this. Like, it looks like some just any photo. But people usually want models to generate images of high quality, very aesthetically pleasing, with like wow, so you can send it to your friends or publish somewhere. And that's why we have a second training stage called fine-tune. We gathered manually some small data set of 1,000 images of exceptional quality, and we train our model a little more on these exceptionally good images. And the same model, after this small fine-tune, produces images like this on the same prompt. And like in large language models, we also have reinforcement learning stage where we compare different generations of the same model, and people compare them, and we align this, we train our model on a human feedback. And so the same model, after this stage, we can produce images like this with the same prompt. Usually, fine-tune, it increases general aesthetic of image generations. And reinforcement learning, it can improve relevance to the textual prompt and make image more detailed. Like here you can see, even on the second image, it looks even less defective than the first one. And the third one is much richer than both of the first ones. And another example, also the third one is very rich in details. But I said about that we can compare images to get which one is better. How do we do that? We take a popular method. We just take two models. We take some small data set, maybe 500 textual prompts, and generate images using these two models on all those prompts. And then we give people pairs of images plus prompt, and they can choose which model is better based on the instruction. And the instruction can say that choose an image which is more aesthetically pleasing, choose an image that is more relevant to the prompt, which is more complex, or which is less defective. And we have all these four aspects for assessment of how a model performs. It's actually quite interesting because assessors, they can really be excited about this comparison. For example, here, assessor learned that our model generated an image based on the prompt of white American bulldog, but it's actually a British bulldog. And they even had a discussion like what they need to choose, like from two models. But it's really that it's an English bulldog, not an American one. Very interesting. Yeah. And so it's not all that easy because we train our model on a large infrastructure. We have hundreds of GPUs on several servers. They should be interconnected with fast network. There are lots of experiments to get some features in the next version of the model. And for example, we had one model of large scale that quality of it was lower than the previous model version, even though our small experiments showed that each feature that we added to the new version, it was better than on the previous version model. But in the end, not every experiment can scale up to a large setup. Yeah, infrastructure may not be ready. For example, in our training, we usually take like 2 gigabytes per second from the data platform of data. And one night, when I wanted to go to sleep, I got a message that, hi, you're reading too much data from the cluster. And our data cluster was not feeling good about our training because we read too much data at the same time. And there are lots of more problems, like that we can't prevent. For example, hardware problems, GPUs can break, like servers can break, network can break, and it all causes some downtime in training. And there are there can be lots of bugs in external code, and there was bugs in our code that can also, prove worse for the final model. Another interesting example of the problem is that in that example. Yeah, so we trained our model. This is a step 550,000. We trained it more. It's 100,000 more steps. And then on the next evaluation, the model started generating images like this. They had like this defect of horizontal lines. And this is our metrics. They all went down. And we needed to stop our training and figure out what the problem is. And the more images on the top is images from a good step, and on the bottom it's examples from a degraded model. It's actually quite interesting, but not like in general, because you can't get images other than like those ones, but they have interesting style. And the actual problem was that we used float 16 for training our model, and when model weights started to get close to float 16 minimal or maximum values, started to produce degraded images like this. And after that, after we found out that this was the problem, because it's not really easy to figure out if you don't know it, we switched to bfloat 16, which has much higher range, and the problem gone. So we backtracked a little to a stable checkpoint and continued training from it on bfloat 16. And it went well after that. The last thing I wanted to show you, which I really like, is how the model trains, how model generations changes during training. So here, on the left, it's original images from the trained dataset. And on the right, it's supposed to be model generations on the descriptions on the images on the left. You can notice two black squares. As I said, we can't really prevent bugs because it's human error and everything. So that was a bug in our visualization. I suppose on the next slides there will be much more interesting, so I decided to leave them in. The bug was if you're interested on unconditional generation, like when we don't give any prompt to the model. So for now, it's just pure noise. Like, model doesn't know how to generate an image. So we train it for 5,000 steps more, and we can already see some shapes. Like, for example, here it's some car, a shoe on the top left, but still quite noisy, and you can really figure out anything here. Next, 5,000 steps, and you already can see shapes without noise, like a car. But what I really like about this image is that's supposed to be a cat, but it's some white mess, and it's supposed to be a fish, second on the bottom row. But for now, it's just some colored mess. So we train a model more, and this white mess got some eyes, so it already looks like some cat. And everything starts into getting into these details on the original images. And so we train it more and more. And after 40,000 steps, that's already pretty good images. Kind of defective, but already not what was in the beginning. And let's skip forward a bit. After 150,000 steps, those images are already pretty good. You know, you can find images like that in the internet, not AI generated. But this is only a force. Like the model needs to train for until 1 million steps. So it's only a beginning. Okay, so that's everything I want to tell you guys. You can try our model Yandex.Art at Chedevrum AI based on this QR code, and I'll be glad to answer your questions.
Thank you very much. I'll just join to help a little bit. Do we have some questions for Eugene? Yes, here, please. Microphone goes here in the fourth row. Yep, here.
Thank you for boom, boom. Okay. Thank you for the presentation. I have the following question. Like, these generation models have problems with generating complex prompts, like with complex reasoning. Like, if we had a cat flying towards sun with person sitting on it, what block is responsible for bad reasoning of complex prompts?
Thank you for your question. Usually, there are several parts in it. First of all, as I'll keep fighting my slide while I tell you that. So the first one is the dataset. So we want our dataset to contain descriptions, very descriptive. And if we have descriptions like you said, like complex one, like someone flying over something, the model will learn from it. But if we don't have it, the model, it would be hard for it to generate something like this. The second part is that we can use reinforcement learning with prompts like you said to iteratively improve our model understanding of these complex prompts. So the block is data, usually.
Just please.
Yeah, thank you so much for the talk. So my question is, how do you decide when to stop the training? And also, you mentioned that you pay attention to aesthetics. And to me, that sounds something very subjective. And that can introduce a lot of bias. So don't you think that that can be a problem?
Yeah, thank you. There's two questions, right? So the first one was, when do we decide to stop training? There's this image, like we have a monitoring of our metrics. And usually when metrics started to plateau, like they don't change anymore, we can stop the training because it doesn't really change. So it's the first question. Second question about aesthetics. Yes, that's right. It's kind of a difficult question. That's why we have 4 different aspects on which we compare our images, and they have a really detailed, like A4 instruction about how do we need to choose a more aesthetic image or a more complex image. So yeah, we kind of formalize that. But of course, people can think differently, so we always change this instruction to, be more flexible.
Thank you. Any other questions in the room? Let me see if I see any more hands for now. Yep.
Yeah, there's.
Yeah.
Hello, thank you for presentation. Just one question. What about copyright? Because everything what is on the internet is not free. How do you filter images based on that?
Yeah, thank you for the question. So we use image database from search engine, which already just indiscriminately crawls all of the internet, and some sites have like robot.txt that doesn't allow it. So we already filter out like most of the images that are not allowed to use in training. So we have another part in that we don't maintain in a database. So we take only images that can be used for training. It's not my scope of work, so we take something that we can use.
The internet is, I can go have a website and upload whatever I want. And if you crawl it, if I don't say it's free, then you don't know it's free. Maybe I took it from some other website and I uploaded it, but I'm...
Yeah, it's a complex, problem. But right now, we use only legally images that we can legally use. But I don't maintain this part of the pipeline, so I can go into the details.
Hey, yeah, I wanted to ask about, so diffusion models have been out for like a year or two already, like Stable Diffusion and Midjourney and so on. And they have been improving over the years, like new versions coming out. So I'm just wondering, what do you think are the main things that improved, like in the newer versions? Is it like something from the architectural side, or is it more better data? What do you think?
Thank you for your question. Yeah, so there are several parts of quality on these image generation models. And for example, there is a lot about data. Like I said, we need more accurate textual descriptions. So a lot of it comes from the data. But then there are some architectural choices that contribute to improving the quality as well. So there is no silver bullet. Everything contributes little by little to get huge leaps in quality. So we had experiments that when data helped, when architecture helped, when something else helped, like inference, you can inference your model differently. It all matters.
Okay, thank you.
Let's see if we have another question. Yes, please.
Hello, thank you for your presentation. Generally, language models are known for misinterpreting negations. Do you work with the negations while you are generating images? For example, taking a look at this slide, an orange dog sitting in a grass. If the user tells, do not draw flowers there, how it will react?
Yeah, like I said, we have a huge instruction for assessors to choose images. And we decided that if like these flowers, they are in background, they are not the main subject here. And we don't have anything saying about it in the prompt, so it's not the main thing. But if you have 2 images identical, but one has flowers on the background, but there is no mention of it on the prompt, so we choose the image without flowers. So it's quite detailed instruction, and we have an aspect like you asked in there.
Thank you.
Thank you very much. I think we'll wrap it up here. Thank you, Eugene, very much for your presentation, your answers, and this is a little token of gratitude from the organizer. Thank you very much, and please give a warm applause.
Thank you.
Thank you.